In this important video, we will learn how to define or form a random variable using conditional expected value. In other words, the expected value of something given some other random variables becomes a deterministic value. However, we could use this one to form new random variables. Let's see. So we want to form random variables using conditional expected values, and this technique has lots of applications. So the conditional mean of y, assuming x equal x, is a function of x. So f y of y, given that x is equal x. Okay, so this is the joint PDF fx of y of, let's say, x and y divided by fx of x. So this is a valid PDF for y, but in any case, this function is a function of x. So this one. So this is the conditional PDF. Now, if I write expected value of y, so what I get, expected value of y given x equal x, this becomes integral over y from minus infinity to plus infinity of the value that this y takes on, and then I have to write the conditional PDF, which is f y of y given x equal x, and this guy itself is equal to this ratio, and then the y. So this is equal basically integral of y fxy of x and y divided by fx of x, and then you integrate with respect to y. So y from minus infinity to plus infinity. Remember that here y is dummy variable and it disappears. However, the value of x here, this value of x here and here, they don't disappear. So this guy is a function of this expression is a function of x. Okay, so I denote it by phi of x. And obviously, this for a given value of x is a real. So this is a function from real numbers to real numbers. So this is what we mean here. So now we have a function of x. Okay. So using this function, whatever it is, I could say, oh, this function of x, I define a new random variable, and which is phi of x. So this means that we have to calculate this integral, find this expression of this function in terms of x. This is a function of phi x, and then we could, using this is substitute these after the integration. We can substitute this x by the random variable x, and then this will become a new random variable. So remember that this notation is just do the integral and then replace x by x in order to define a new random variable. So this is how to form a random variable using the conditional expected value. So this notation is abbreviation of these two steps. Do the integral and then replace it by x. So, and then obviously this abbreviation is totally different with this one. So this step is just to do the integral, but then you substitute with a random variable. So here, this x is a random variable. Here is a fixed real number. So this is just notation, and it has a very clear meaning. Now, so what we want to say is that this new random variable has a distribution, okay? So which is defined. So this is z, okay? And we want in this theorem prove that expected value of this random variable, if you do, so therefore when we do this expectation, we have to put distribution of either z or distribution of x, but here you have to put the conditional distribution. So this theorem is it says that the mean of the conditional mean, so this mean is over the distribution of x. The second one is the expectation over the conditional distribution is equal to the unconditional distribution. So this theorem is stemmed from the fact that the joint distribution f x and y, x y of x and y is equal to fx of x times f y given x of y given x. Now let's see how we can prove this one. This theorem. And this theorem is very important because the mean of the mean is equal to the mean. This theorem is very basic and is the basis of martingale theory, which is an alternative to the probability theory. So it's kind of like they are equivalent. This theorem, it can be easily generalized. So instead of random variable y, you could have any function of x and y. Sometimes you can generalize also the condition, and we want to show that. So the proof is very easy. The first expectation here is equal to this one. So we have to put the value that this guy takes on. So we put this one, and then because x is determined here, so x is not a random variable, y is a random variable, so I have to put the distribution of y, but because I have a condition of x, I put the conditional distribution of y given x. Okay, and then I define it like as a function. Okay, now here I define a new random variable and I replace this one by x, and then I calculate expected value of these. Here I have to put the distribution of x, and this guy is going to be equal to the value that this function can take on, is this one, and times distribution of whatever is random here, which is this one. So I have this one. Now I could take this psi x, this expression, the first integral, and then plug it in here. So I get one integral inside another integral. So you get this is equal to this part is equal to this one based on this one, and you have this integral. So this fx of x is, because here the integration is over y, and this x is both x and y, because we have two dummy variables. Okay, this is x, and because y and x are not interrelated and these boundaries are not, so I could put this fx inside here, and then I have the fact that fx of x times fy given x of y given x, this is equal to the joint distribution fx y of x and y. Okay, so I put it there, and then this product of these two becomes the joint PDF. So this is what I did. I put it here, and the product of these two guys is equal to this one. Now, if you look at this expression, this is nothing more than, this is the joint PDF of x and y, and this is expected value of g of x and y, because the definition of this one was that the value that this guy takes on times its joint PDF, and that's it. So the proof is complete. So the proof of this one was easy. We proved a more general case as a proof of this one.